Hello everyone, good morning. Nice to see you all today. Today we will try to finish it earlier because I have meetings and also another events going on now, right? Okay. This week we will enter to the topic called stability. So stability, as we know previously, if you still recall for the steady state error, when we try to find the steady state error, some of the problem will always ask you to first check the stability. Okay, so what it means by stability of a system. Okay, the goal for today is to evaluate the stability of a system so that if the system is stable, then only we will do the necessary control of it. If the system itself at the beginning is not stable, okay, then we cannot control. That's why we first we must know whether the system is stable or not, right? So here you can see that we have previously discussed about how the S-plane, okay, where the locations of the roots actually lying, and how what is the characteristic of the time response, okay, the corresponding time response according to it. Okay, so you can see that when the pole is lying along the imaginary axis, then we will form like undamped situations. Okay, the undamped situation is like it's still stable somehow, okay, but yeah, it's still stable. Okay, somehow it's still stable, but for an unstable system, what happens is that the amplitude will continue to grow over time. Okay, that leads to the that we cannot control the final value of it. Okay, that's why the stability is very important, and it is somehow correlated with the locations of the roots on the S-plane, right? So you can see that, just a recall, okay, when it lies on the imaginary axis, we get the undamped type of response. Then when it is on the S-plane, okay, which consists of the roots consists of the real and the imaginary values, then we will get the underdamped. Okay, when it is lying at the same value of the real axis, okay, then we will get a critically damped. And finally, when we have two distinct real roots, then we will get overdamped. Okay, so this is the characteristics that we have observed previously, right? And we will notice that most of these roots now, okay, is lying on one side of the S-plane. Okay, they are lying on the what we call the left hand plane, okay, or left half plane of the S-plane, right? So whenever it lies, all this root lies on this side, okay, we notice that the response that we get actually so somehow is stable. Okay, we get something over here. Okay, and the worst case is the undamped, okay, which we still consider that lying partly on the half of the left half plane, right? That's why this is the stable zone. Okay, what happen if this pole now shift to the right half plane? In that case, for sure it will cause the situations to become unstable. Okay, so this is why the S-plane is important for us to visualize the stability of a system. Okay, so how we definitions of stability. So stability is again the most important system specifications, okay, such that if we have an unstable system, we cannot control or design, okay, to obtain the desired specifications or steady state error requirement. Okay, So here we will divide the stability again into three types. First is stable, second one is unstable, and the third one is marginally stable. Okay, so as we have seen from the previous graph, okay, so we have seen the stable and the marginally stable part. Okay, whereas the unstable is when the time response the amplitude continue to grow as the time approach infinity. Okay, that is the unstable part, right? So for a linear time invariant system, the stability can be divided into these three types. Okay, where the stable refer to when the natural response system or of the systems actually approach a zero line, okay, or a steady state line, okay, as the time approach infinity. Whereas for a marginally stable, we have the natural frequency of our system that don't decay as well as don't grow. Okay, it will remain oscillating, okay, about a value. Okay, that's why we can see that the undamped type of response will give us a marginally stable stability, whereas when the natural response of the system actually grow beyond, okay, the boundary, okay, without a boundary, okay, without a bound, as time grow, then we call that as an unstable system. Okay, so we can see that all these definitions purely depends on this natural response. Okay, natural response. Okay, remember we have two type of response. First is the force response, the force that you give to it, and the second one will be the natural response of the system, where how the system will react, okay, naturally. Okay, so that is the natural response. So we can break the total response into the force response as well as the natural response. Okay, but then in the definitions we always use this natural response because this force response itself is what we control. Okay, when we control the so-called input to our system, the type of input we are providing is actually steady. Okay, we may give a step type of input or an impulse type of input and so on. Therefore, this effect or the response of this force part eventually will die out. Okay, therefore as time grows, the only effect that remain in the system would be the natural frequency, okay, or the natural response of the system. Okay, therefore the definitions previously mainly depends on the natural response itself. Okay, so now we have another definitions for stability based on this what we call BIBO. Okay, so BIBO is actually called as bounded input, bounded output idea, right? So what happens is that since this force and the natural response actually being combined as a total response, most of the time we may be hard to break them out, okay, separately, explicitly. Okay, therefore this BIBO idea is that we know that using a total response itself, okay, BIBO idea is that if the system is stable, therefore for every bounded input, okay, we give a range, okay, which is not unsteady type of input, for sure we will get a bounded output, right? For an unstable type of system, even though we give whatever type of input, bounded or unbounded, okay, mostly we will still deal with bounded. Okay, whenever we give any bounded value to the system, it still give us an unbounded output. That would tells us there is unstable natural response to the system. Okay, this is the idea of the BIBO. Okay, So based on that, now we will try to identify the stability, okay, purely based on the locations of the roots itself, okay, that we have known previously, right? So recall that the natural frequency of a system can be applied, and we can actually plot the natural frequency of the system into the S-plane, okay, which is we have covered previously. Therefore, as I've mentioned earlier in these sessions, we notice that the left half plane, okay, over here will yield either exponentially decay or damped natural response. Okay, this is where you can see that as long as it lies on the left half plane, it will give us so-called a damped natural response. Okay, eventually it will decay to zero as the time approach infinity or reach a steady state value. Okay, so in other words, we will say that a stable system will have a closed loop transfer function with pole only on this left half plane, right? So again, we will notice that in this discussion, we will start to so-called focus more on this type of closed loop system, okay? Because by using a closed loop system, eventually we can tune our system to meet a certain performance that we want. Okay, this is why we usually need a feedback type of system in order to help us to tune, and at the end of the day we will say to design a control system. Okay, in order for us to have this type of idea, we must able to modify the gain or to add a controller to it, okay, to control the behavior of this so-called natural response of the system. Okay, that's why now our focus would be on mainly on this closed loop transfer function. And even though it is a closed loop transfer functions, when we simplify them into a single block diagram, okay, a single block, then this closed loop transfer functions eventually will form a second order transfer functions similar to this, right? Okay, therefore from this we can get our or we can evaluate our stability of the system. All right. Then also from our previous experience, we also know that if the root is lying on the imaginary axis, then we will have this characteristic of undamped system. Okay, so when this happens, therefore we will get the marginally stable system. Okay, again we would say that the marginally stable system will have a closed loop transfer functions with only imaginary axis pole. Okay, imaginary axis pole. Okay, we don't have any real axis pole of multiplicity of one, meaning to say we have only one root, okay, on that particular point, okay, in the imaginary side. Okay, and the pole is on the, we still consider the half left half plane, okay, since it's in the boundary. Okay, therefore we still consider that the marginally stable, even though it lies on the imaginary, the pole we consider still in the left half plane, and only imaginary axis pole with multiplicity of one. Okay, only one point, right? Not many points at the same, let's say in this case J3, right? So based on that idea, okay, then we know that whatever lies now on the right half plane will give us a pure increasing exponentially type of response, okay, and we try to avoid that kind of system, okay. So here the natural frequency will approach infinity as the time approach infinity, okay, for when we have these poles lying in the right half plane. Then also even though we have a positive, or in other words, okay, if it lies on the right half plane, meaning to say if the pole itself consists of a positive real part, then the system is unstable, okay, meaning this is the important characteristic of knowing whether the pole is on the right half plane or not, right? So if it has a positive real part of the pole, then for sure it is unstable, right? Also, if the poles have a greater than one imaginary axis, okay, remember previously, multiplicity of 1, okay, only 1 point at J3 and 1 point at minus J3, let's say. If we have 2 points lying at the same point, J3, 2 points or multiple more than that, then again we would say that would cause the system to be unstable, right? So therefore an unstable system can be defined as the closed loop transfer functions with at least one pole on the right half plane and or many poles of multiplicity greater than one on the imaginary axis. Okay, so this is the definitions of the stability that we intend to check today, right? So this is the comparisons between the stable and an unstable system. Okay, we can see that if it is stable, then it will eventually reach a steady state error or a steady state value, whereas for an unstable system, okay, we can see that from this system where it has a pole on the with a positive real axis and real value or real parts, okay, then the system will now continue to grow, okay, without a bound. The problem is that if we have this kind of system, okay, we intend to analyze most of the time with the what we call a feedback control system now, right? If it is an open loop system, then we can get it directly, okay, very straightforward. But when we start to deal with feedback type of system, then we first must convert it or simplify it into a single block, right? We will name that as TS, right? So this is a single transfer functions, okay, to represent this feedback control system, okay. And we can see that in this feedback control system itself, it consists of S to the in the order of 5, 4, okay, the highest order is 5, okay. The questions now, is this system stable? Then if we look at this, then we will have the so-called tendency to say this is a very hard questions, okay, because you have to factorize, okay, to solve this problem, okay, to get all the since this is in the order of 5, then you have to get 5 roots, okay, which is difficult to solve, okay. Even if you use computer, okay, it may give you some error, maybe, okay, we don't know, right? So what happens is that it is difficult to solve, to identify whether the system is stable or not. Therefore, if the better way is that if we have a method to actually know, okay, because the pole is mainly depend on the denominator, the bottom side, right? So if we have a method that actually tells us how many poles on the left hand plane, how many poles on the right half plane, then that should be sufficient for us. Okay, we don't actually need to solve for the exact roots. Okay, and that is our main intentions today, right? So a sufficient conditions for a system to be unstable is that all signs of this system itself, okay, on this system itself, on the denominator signs first are not the same. Okay, so this is the first criteria to identify such that they are unstable. And also, if the power of S are missing, okay, so if you have S5, 4, 3, 2, 1, then it's okay. If there are something missing, then the system can be unstable as well, okay, or at best maybe marginally stable. So we try to use these ideas to give us an insight, okay, without solving for the roots, okay, especially when the days we don't have computer to help us. Therefore we need a better way to actually analyze it. Okay, imagine this is only in the order of power 5. Okay, sometimes if our system continue to grow, you have multiple block diagrams combined together, then the order will become greater and greater. Okay, therefore this is what we intend to solve. Okay, the one of the methods is we call it Routh-Hurwitz Criterion method. This is a mathematical method that have been developed by these two great scientists, okay, or mathematicians themselves. Okay, the importance of this RH method is that they actually trying to solve it to identify where is the locations of the roots, okay, without actually telling you what is the exact value of the pool or the solutions. Okay, so there is this mathematical methods, okay, that we adopt, okay, to solve for our purpose, okay, to identify the locations of the pool, whether on the left half plane or the right half plane or on the imaginary axis. Okay, these are the three main part that we would want to know, okay, to identify whether the system is either stable, marginally stable, or unstable, right? So we can use these informations in the design, okay. But if we want to do analysis, okay, where we start to do all those calculation, then this method may not be good, okay, because when we want to do analysis, we want exact value to calculate, right? But when we want to design, okay, design means you have certain parameter that is unknown, okay, maybe you have a K or A or B, right? Then these methods will be good, okay, to know where is the locations of the pool, right, to get whether the system is stable or not. Okay, so we will go through so that you get the better idea of what I mean later on. Okay, so these methods require two steps. The first one will be to generate the data table, okay, we call it a Routh table, and the second one is to interpret the Routh table in order to tell us how many pools are actually on the left half plane, right half plane, and on the imaginary axis, the J omega axis, right? So I hope the intentions of this is clear now. So we will move into the Routh table, how we can generate a Routh table. Okay, so assuming you already have the equivalent closed loop transfer function. Remember, originally this is a closed loop system. We simplify it into an equivalent closed loop transfer functions. Okay, that is the first step. Okay, and we try to analyze this equivalent closed loop transfer functions, right? Since this is the difficult part of it. All right, so once we have this now what we do is we start to label, we check the highest power or highest order, okay, on the denominator. The main pulls always on the denominator. Upper side is zeros, remember? So therefore we only take the lower polynomial, okay? This lower polynomial will be our main analysis, our analysis focus, okay? So first take the highest power of this denominator, then we start to sort it in the descending order. So we have S4, S3, S2, S1 and S0. Don't forget we have S0, okay? We just have to get the highest one, then we just order it down, right? So all the way down, okay? Then after that, we will start with the coefficient with the highest power, okay? So this is S4, then we have the A4 here. So what we do is that we will start with A4, okay? Then we jump A2, A0, right? Then for the second row, we will start with the next highest power, okay, which is A3. Then we jump down to A1, and if nothing, then 0, okay? So if to helps you to memorize easier, then we just have to rearrange in the zigzag, okay, up or down, okay? So 4 3 2 1 0, then nothing here, okay? Nothing means 0, okay? So you can see that 4 3 2 1 0 as such, okay? So we can arrange it in this way, okay? And we have started with our basic rough table, right? So next, to fill up or to complete the rough table now, what we need to do is to put in those value, okay, by doing a certain operations, all right? So the operation will depends on the entry or the value for each of this cell would be the negative determinant, okay, of the previous two row, okay? So the previous two row, okay, divide by the entry of the first row, okay? So divide by the entry of the first row, which is just right above it, okay? Entry of the first row just right above it, okay? So same thing for this, right? So maybe we just go through it into details so that we can visualize it, okay? So this entry itself is a negative determinant divided by the coefficients just right above it, okay, on the first row, okay? Therefore I highlight the red one is here, okay? Just divide by it, right? Then how to get this determinant? This determinant actually consists of these two parts, okay? So the first column of the determinant will be the first column of the previous two rows. First column, remember, only the first column, so we have A4, A3, okay? Whereas on this side would be the one next to it, okay, next to it, but still the two rows above it, right? So we have A2, A1, okay, we put it here, right? So to solve this determinant is just A4 multiplied by A1 minus A3 multiplied by A2, right? So how to solve determinant, you just check it out, right? So by doing this, we will get a value, right? Same thing to get for the second entry, we do the same thing, right? Remain first column, okay? The first column of the row above it, okay? So we have A3. Then what happened is that okay, so this will remain over here, okay? The only thing changed in our determinant is that the first column remain unchanged, okay? It's still A4 over A3. The only changes would be this second column, okay, which we shift to the next one, okay, shift it to the next one, so which is A0 and 0, okay. So as we can see for the next one, okay, we maintain A3, but then for the first column remain the first column for the two row, the previous two row, plus this one, the green color will shift to this side, okay, where you don't have anything, so you just put 0 0. Since this is 0 0, very straightforward, multiply by 0, we get 0, right? So that is how we can complete it. So do the same thing for the second one. So this one will now consist of A3 and B1, A3 B1, okay, A1 B2, A1 B2, okay, and this one is B1, right? So same thing here, A3 B1, then here 0 0, divide by the first column of the previous row, so which is B1, right? So 0 0, again you get 0 0 as well over here, okay. Then continue to do it, okay, for the until we reach the last row, then we have completed our rough table, okay. So once we have completed the rough table, now the next task would be how to interpret this table, okay, in order to get to identify whether the pole is lying on the left or right or in the imaginary axis. So this Routh-Hurwitz criterions identify that the number of roots that are in the right half plane, okay, is actually depends on how many number of sign change, okay, from positive change to negative or negative change to positive, or in the first column, okay, of the rough table. So if we know how many time of change, then we know how many poles actually lying on the right half plane, right? That is the main idea. So if the system is stable, then for sure there is no sign change, okay, that result to this existence of the pole on the right half plane, right? So we will go through an examples. Here, such that we have this closed loop system. First thing first, before we generate the rough table, we must convert this into an equivalent closed loop transfer functions, okay. How to convert it? We just apply the formula that we have learned previously, right? So once we have this transfer functions, what we can do next would be completing the rough table, okay. So first thing, we can see that the highest order is 3, so we will put 3 as 3, 2 as 1 as 0, okay. Then we fill in the coefficients of in the vertical zigzag way, okay. So this is 1, then this is 10, this is 30, this is 1, 10, 30, right? So we have, okay, we have this 1, 10, 31 and 1, 0, 3, 0, right? Then once we get this one, actually in the rough table we can further simplify, okay. For the same row itself, if we can do a factorizations, in this case we can see that we can factorize with 10, okay. So if we divide it with we don't never divide with a negative, because remember, we don't want to change the sign, okay, by ourselves, okay. We can only change the value, okay, by factorize it, okay. So therefore we will divide with a positive value, okay. So in this case we divide by 10, then we get 103, okay. If we don't get any factors, then never mind, okay, we will continue with that, right? So once we have that, we complete our rough table, and now we observe whether there is sign change or not on this first column in our rough table. So in this example, we can see that the signs change, there is one from positive to negative, then from negative back to positive, okay. There are two sign change that we can observe for this. Therefore for these situations, we would now know that there are two poles actually exist in the right half plane. Okay, you see, by using this method, we actually can know that how many poles actually how many poles actually lies on the right or left half plane, okay, or the left half plane, okay, accordingly, right? So here we know that since there are two sign change, there are two poles exist in the right half plane, okay, and we know that right half plane is related to unstable system. Okay, so immediately we know that this system is unstable, right? So it's very quick to help us to actually identify the problem. When we deal with the rough table, they may happen with two special case, okay, which deal with zero, because we have to divide by a number. Okay, if that number is divided by zero, then we have the problem occurs. Okay, so there are these two special case, okay, when zero occurs either on the first column, because remember we always divide by the first column number, right? So we always divide by the first column number right above it. Okay, so first column number, when it becomes zero, then problems occur, so we need to deal with that. Or in another special case is that the entire row is zero. Okay, then what it tells us. Okay, so there are two special cases that occurs. Okay, so first we deal with the first case first. Okay, when the zero occurs only in the first column. Okay, so how we can deal with it is we have again two methods. Okay, first method is we assign an epsilon, okay, to replace the zero. Okay, when we reform, okay, we calculate, when we get zero, then we assign it with epsilon instead of putting a zero. Then we continue putting the epsilon in our calculations. All right, so this is a way to do it. All right, so we assume the zero to be epsilon. All right, now because our main intention is just to know whether there is sign change or not, so this epsilon will help us by taking the epsilon value approaching zero. We can take a side like the epsilon zero is positive, or when the epsilon value is negative, okay, how many sign change occurs, right? So once we assign with the epsilon, now just go through these examples again, right? When we occurs with the zero, so we will complete the rough table and we get this, right? So what happened is that we notice that there is a zero over here, we replace it with epsilon, okay, we get this. Now when we try to interpret, we have to now assign, okay, whether the sign for the epsilon is positive or negative. Okay, so let's say we take the epsilon value as positive, then we see that 1 is positive, 2 is positive. Epsilon value, we take it near to maybe positive 0.001, still positive. Okay, then if we put this value as positive, we can see that, let's say positive 1, okay, you can assign a value to it, right, in order for you to identify what is the sign for it, right? So if this is a positive value, let's say you take positive 1, you replace 1 with it, so 6 minus 7, negative, divide by 1, you get still negative, right? So therefore you can assign a negative sign to it. Okay, then once this is negative, then again put a small value to it, negative 1 or negative 0.01. okay, negative 1, okay, you just use your calculator or whatever, okay, put put a small negative value to this to replace this epsilon, then again you will get a value which in this case is a positive, right? So you can see that there is two sign change occurs, okay, when we assign a positive small value of epsilon. Then again, since there are two sign change, positive to negative one time, negative to positive another time, therefore there are two poles lies on the right half plane, okay. Whereas for the negative side, when we assign a negative value to our epsilon, okay, same thing, okay, if we put negative 0.01, then you will see that now it turns to positive. Again, you can see that two sign change, okay. So immediately you can see that they are consistent, okay, telling us that there are two poles lying in the right half plane, and we know that the system is unstable, right? So this is how we can do it. A second method to deal with this zero only in the first column is we use a method called polynomial with reciprocal roots. Okay, what it means is that reciprocal is 1 over something, right? Okay, so if our root is 1 over a number, okay, which is less than 1, then we can actually reverse the order. Okay, so this is the idea of this method, that if we take the reciprocal of roots, then the original polynomial will have the same roots distributed according to the left half, right half, and the imaginary. Okay, so therefore we would use this reciprocal roots to solve our problem, okay, when zero only in the first column occurs. Okay, this conditions occurs. So here we will take the reciprocal 1 over d, for example, okay, for instance, to replace for the s. Okay, so originally we have a polynomial, okay, with an order of Sn, okay, then we take this, we just replace it, right? Then eventually we can factorize this out, okay, and rearrange. We will see that now 1 a minus 1 and so on, okay. And again we can see that the coefficient, you see the coefficients after we take reciprocal remain the same, okay, 1 an minus 1 and so on, okay. So therefore we can see that even though we take the reciprocal roots now, okay, but then the coefficients doesn't change. And if the coefficient doesn't change to the polynomial, meaning to say the number of pool on the right half, left half, and the imaginary will remain the same, okay, which is our intentions to know, okay. Therefore by taking this, we also do not actually disturb the systems. The only difference is that the coefficient is the same, but then the order now change, okay. We just reverse the so-called coefficients arrangement. Originally this one highest order Sn is 1 here, okay, then we just reverse it, okay, the order is this, okay. So just take an examples for the previous case, okay. So our previous case, okay, we know that at the S3 itself this will become 0, alright. Okay, let's go back, okay, let's check. Alright, so previous case, when we reach the S power 3, we have a 0 value for this column, right? So what we do now, okay, when we reach that kind of situations, using a second method, we just rearrange this polynomial, okay. First you can try, okay, until you see 0, you reach any 0 over here, then you just redo, okay, by taking the reverse order of the denominator, okay. So we will reverse the denominator. Instead of still S5, S4, S3, S2, F1, but then this order we now reverse 3, 5, 6, 3, 2, 1. Okay, we just reverse the order of it, okay, based on the previous idea. Okay, order, the coefficients remain the same, but the order change. Okay, you can see the parameter, the S, change positions, right? So this is the idea. You just reverse the order. Now do the same thing using this new reverse order polynomial, okay, to our rough table. So now we put 3, 5, 6, 3, 2, 1, right? So once we have this one, you do as usual, completing the rough table. Eventually we will notice that it doesn't give us any 0 over here anymore. Okay, the 0 may be shift to the other side because the order have changed. Okay, but nevertheless we still see that they are, when we interpret, we still see that there are two sign change. Okay, positive to negative one time, negative to positive one another time. So two sign change, and we know that there is two right half plane to our system. Okay, so therefore it's consistent with our previous methods, right? Two right half pole and the system is unstable. Okay, so that is the another methods to solve it. Okay, so another special case, we call it as special case number 2, where the entire row coincidentally becomes 0. Okay, this occurs when the factor of the polynomial itself, the polynomial itself actually is a factor to the original polynomial. If this happen, then we would encounter with this 0, 0, 0. The whole row becomes 0. So even though if it is the whole row becomes 0, if you reverse the order of the polynomial, it may not solve your problem as well. Okay, somehow. Okay, because eventually you will still get 0, 0, 0, right? So to deal with this, we have to break this polynomial into two parts. Okay, so first we will give you the idea first, right? So here we have this so-called closed loop transfer functions given as such, and eventually these transfer functions give us 0, 0, 0. Okay, so what we can do in this case is that we will try to break them into two parts. Okay, the first part we will do as usual. Okay, until we reach the row of 0, we will put a remark here. Okay, in the exam you can put a remark here. Okay, when you get 0, 0, 0, you put a ROZ. Okay, represent row of 0. Okay, to our system. Okay, and when this is row of 0, what we can do now to continue to solve for this is that we will form an auxiliary polynomial, meaning to say we will form another new polynomial instead of the original one. Okay, we will form an auxiliary based on this, the previous row of it. Okay, the row immediate above the row of 0. Okay, so here we get 168, right? Because we can simplify this 742 56 into 168. Okay, so we will use this 168 as our new polynomial, okay, to continue. Right, so what it means is that this is s to the order of 4. Okay, meaning to say this is the coefficient for s power 4. Alright, so we have s power 4. Okay, then this is 6 6 is the coefficients, and the value or the order would be, remember, this is 4, then this is 3, and this is 2, so this would be S2, okay, and this is 1, this is 0, okay, S0 means 1, right? So 8. So eventually we can write in the sequence that we have S4, S2, S0, right? If the coefficients being defined by the row above it, okay? Just have to check what is this order. If this is S6, then you have S6, S4, S2, S0, okay, and so on, okay? Right. So once we have this auxiliary polynomial, then what we need to do now is we differentiate this polynomial, okay? We differentiate, then we will get S, differentiate respect to S, okay? Then we will get 4S3, then this one multiplied with this, then we get 12S plus 0, okay? And this would be our new value over here, okay? We will now assign this 4 over here, 12 over here, 0 over here, okay? Instead of all 0, we put a row of 0, we try to form this, and we differentiate the auxiliary polynomial, and then we continue with the new value, okay? So once we have 4, 12, 0, then the next we just do as usual, right? So we have we do with 3, we will get 3, 8, 0, and so on, okay? Just solve accordingly, okay? Since we have 4, then yeah, we just solve accordingly. We have 1, 4, we get the determinants and so on, right? Just repeat accordingly, right? Okay. So again, when we solve, we can simplify 4, 12, 0 to 1, 3, 0, right? Okay, so it's a way to solve it, okay? So here, once we get this, again, when we interpret, we see that 1, 1, 1, 3, 1 over 3, 8. No sign of change, okay? Meaning to say, system is stable, okay? So this is the idea behind it. Right. Now, further into the case, to further dissect the interpretation itself, okay, we will now see what actually happened, right? So when an entire row of 0 appear, this is because of there are polynomial that are factors of the original polynomial. You may have a s power 4 power 3 to 1, okay? Somehow one of the polynomial is actually the solutions to it, right? We say a factor to it. Therefore, it causes the table to have this so-called row of 0, right? So, and we also note that even polynomial, okay, this is a terms for a polynomial, okay, which have these characteristics, okay. So this even polynomial will have roots that are symmetrical about the origin, okay. Remember, this is our S-plane, okay. So eventually, if we get this even polynomial, then it is a symmetry roots that occurs on our S-plane, right? And it's symmetry about the origin. Therefore, if we have a point at point A, okay, then the other point would be on the other side, okay, with the same value. One is positive, one is negative, right? If we have a point over here, then we have a conjugate, okay, which is on the other side, okay, which is again symmetry to it, right? So remember this idea that whenever we come to a row of 0, we will eventually meet this so-called even polynomial, and the even polynomial will have a characteristic that they produce roots that are symmetrical about the origin, Okay, so we further to our interpretations now, right? Previous examples, we can see that at this particular sections, okay, this is our so-called auxiliary polynomial, right? So the one in the red color dotted box, okay, would be our auxiliary polynomial, and this auxiliary polynomial is actually the factors of the original polynomial, right? So you can write it out. So remember, this would be the factors of it, okay, because of the row of 0, right? So once we know this one, we need to say when we differentiate and put it here, okay, the red value, whatever we analyze after that is actually all about the even polynomial. We are not testing the original polynomial anymore, right? So we come to a point where we have two sections. One is the original polynomial, and when we come across a row of 0, the one before that will represent a factor to it, and what we do next, okay, after we differentiate, is the test on the even polynomial, okay? And we know that the even polynomial have a characteristic that it is symmetry about the origin, right? So it is symmetry about the origin. So now, how we could interpret it, okay? So from the even polynomial, okay, at row s power 4, okay, down to s0, okay, so this would be the, we call it a test on the even polynomial only, okay, not the original anymore, because we have transformed it, right? So therefore we check, okay, 1, 1, 3, 1 over 3, 8, okay, so 1, 1, 3, 1 over 3, 8. So this test itself tells us that in this even polynomial, in the auxiliary polynomial or the even polynomial itself, there is no sign change. And if there is no sign change, meaning to say everything would be on the left half plane, okay, no right half plane, right? And then because of the requirement of this symmetry, remember, whenever we see a row of 0, meaning to say there is a symmetry problem, okay, it must be symmetrical about the origin, okay, since everything must be on the left half plane, okay. If we have a root over here, is it possible that we don't have another root on the other side if it is symmetrical? It is impossible, right? So therefore, if there is no sign change when we meet the row of 0, meaning to say the roots actually lies on the imaginary axis, because when it lies on the imaginary axis, it still satisfies the symmetrical, okay, it's still symmetrical, but no poles actually lies on the right half plane, okay. Therefore, in this case, okay, we would say that because of the requirement of this symmetry, there are no right half pole, no left half pole would be present, okay. And because of that, we know that this is S4, there are four poles related to it, and all these 4 poles will now lies on the imaginary axis, okay. So this criteria of symmetrical is very important, okay, when we deal with the row of 0, right? So the remaining would be the total, okay. So the remaining would be the one before we reach the row of 0, okay. So before we reach the row of 0, there is no sign change also, okay, only deal with one order, okay. So when we actually sum it up, okay, total them up, okay, so you just check the locations of the right half plane pole, left half plane pole, and on the imaginary axis, okay. For the even polynomial, okay, from here, this is power 4, so there are we are checking 1 time, 2 times, 3 times, 4 times. So there are 4 roots that we are dealing with, okay? And these 4 roots, we have concluded they are on the imaginary axis. Whereas for the others, okay, which is before the row of 0, okay, then we have only we are checking 1 time of sign change, and that sign change doesn't change, right? Therefore, we know that that is a first or 1 order pole, okay, and it is lying on the left half plane, right? So in total, S5 total 5 order, so we would expect 5 pole, and the number of pole would be how should I say? Okay, so the total, sorry, I think I mistake. So the total would be 1 left half plane and 4 imaginary over here, okay? So eventually, since there are 4 imaginary, okay, and on the imaginary axis, therefore the system is marginally stable, okay, marginally stable. Alright, so this is how we can interpret it. Alright, so now come to the stability design, okay? As we say, these methods are very useful for design, but not really on the analysis, okay? What we did previously is to analyze, okay, to give you an idea, okay, how it operates, okay? But the main intention is when we deal with the design, where we have this kind of parameter like K, okay, the gain is unknown, right? But we know that the K is always positive, let's say, okay, then how to design, okay, what value should we put for the value of K in order to get a stable system, okay? So this is how we can do it. First, again, we get the equivalent closed loop transfer functions, okay? From the equivalent closed loop transfer functions, we put into the Routh table, okay? Even though there is K exists, never mind, we just put like K, just assume like a epsilon or whatever, we put in, right? Then we now analyze it, alright? When we analyze it, we know that in order for the system to be stable, there must be no sign change, right? That is the main criteria, meaning to say, if this is positive, this should be positive, and this too should be positive as well if we want it to be stable, right? So meaning to say, this value must be positive, this value must be positive, okay? It's very easy, right? So by doing that, okay, when this value is positive, okay, this must be positive, meaning to say K, if K is less than 1386, we get positive value, right? So our first column will be all positive, okay? But then if this K value more than 1386, okay, then it will start to turn into a negative zone, right? So even though the gain start to increase further, then the system will now turn into unstable state, right? So this is useful when we try to identify the range where the gain will produce a stable system, right? Then when the system itself, when we equate this equal to 0, then eventually we get the K value, okay, which is 0, okay? Then the entire row will be 0 now, okay, 0, 0, right? So if we take this K as 1386, then this will become 0 and becomes 0, and this we call it as row of 0, okay? When we deal with row of 0, we have to do using the special case number 2, okay, we analyze as usual, okay, we take the row above it, okay, now K is equals to 1386, 86. Okay, so our even polynomial will be as such. Okay, 18s power 2, okay, and plus 1386, right? So we differentiate it, we get this value. Okay, once we get this value, we assign as 36, 0, and so on. Okay, so again, this one is according to 1386. All right, so we will notice that, oh sorry, this one will not be relevant anymore because this is 36 and this is 0. You just do as usual, right? So therefore, again, we will notice that any sign change, no, no, and no, right? So in that case, when a row of 0 doesn't involve sign change, means no right half plane pole, and because of that, there are poles lying on the imaginary axis. Okay, so in that case, we can conclude that when k is equals to this value, the system is marginally stable, right? So this would be useful for us when we deal with design. Okay, we know in which range of value of the gain itself will give us a stable system or marginally stable system, right? So this is how we can deal with it. Okay, so again, we have these examples, we do the same thing. Okay, no matter how complex it is, don't worry. Okay, using the rough table, we just put one accordingly, okay, to the order, then put it in. So this, in order to get a stable system, must be greater than 0, greater than 0, right? Okay, so for this criteria, greater than 0 means k must be greater than 0, right? For this criteria, for it to be greater than 0, then this 30 minus 15, k should be greater than 0. Okay, 30 minus 15k greater than 0. Then 30 bring it over 15k, right? Okay, so rearrange, divide over, then this would be in this way. Okay, so k must be less than 2. So these two criteria now we must satisfy, okay, in order for the system to be stable. Okay, so to meet these two, then we will notice that we can actually merge, right? Remember, we can draw a line, right? So 1 is 0, 1 is 2, right? So greater than 2, okay, and greater than 0. Okay, so the area that satisfies these two conditions would be this sorry sorry, okay, redraw, I think something is wrong, right? So less than 2, sorry, greater than 0, right? So the only region that satisfy these two criteria, where these two arrow goes by, okay, would be this region, which is defined by 0 until 2. Therefore, for stability, the k value must be in between 0 and 2, right? So sometimes, again, you may get this type of system, okay, sometimes, meaning to say your k value must be greater than 2. Okay, even though you have two criteria, the 0 is not applicable because you must satisfy all the conditions, okay, for the system to be stable, right? So that's concludes the lessons for today. So any questions? Let's go to questions. Before I forget, the other examples have been attached after this slide. Okay. okay, so you can always refer to additional examples, okay, given in the slides. Okay, after this, okay, you just scroll after thank you slide, there is more examples, okay, that you can go through, and then you can start to try with the tutorial questions, okay. And then after that, since again there is this 1 day gap, okay, we will not have any tutorial class tomorrow, okay, we will have it next Friday is public holiday, next Thursday also public holiday. Okay, never mind, you try it first, okay, and I will inform you when would be the next tutorial class. All right, okay, if no questions, then I would call these sessions to an end. Okay, you can always ask again during the tutorial class, okay, after you try it. Okay, so see you when I see you again, maybe next year. Okay, so for those celebrating, Merry Christmas and Happy New Year. Right, bye bye.